Okay, so we now know about Jacobians and gradients, which are nothing but simple things. It just shows us, okay, for vector valued functions, functions which take in vectors. If we want to differentiate it with respect to the vector, how do we arrange, okay, how will the nth component of my output change if I wiggle the mth component of my input. The gradient happens, when the output, when the function gives us a scalar value, and a Jacobian is the general case where the function gives us a vector. So both the functions take in vectors, but the output can be a scalar or a vector. If it is a scalar, it's a gradient. If it's a vector, it's a Jacobian. So now we want to use the gradients and the Jacobians in doing the chain rule. And what is this chain rule and why do we even want to do it? So as you know, we have x, the input, we have, after going through the different layers in this neural network, we get O as the output. We also have Y as the ground truth, and we have then loss, which takes in our output, it takes in our ground truth and kind of gives us our unhappiness, okay, how unhappy we are with the output O. And then we want to backpropagate, we want to somehow reduce the loss. So we could have easily, reduced the loss, and what are the, if we could directly compute, let's say, derivative of loss with respect to W1, W3 and W5. So this is what we finally want to get to, right? Because if we can get to, say, the derivative of loss with respect to W5, then we can update W5, because that is the direction we want to go into, right? How will my loss change if I change my W5? And what will this be? This will be a gradient. Why? Because loss is a scalar valued function. So, a scalar function. So, its output is scalar, the input is vector, right? And this is what we want to get to then go in the negative direction of this gradient. So, this is a gradient. Now, is loss a function of W? Well, not directly, right? Because loss directly is a function of O and Y is our ground truth. So, I'll just rub this. Yeah. So, what do? Yeah, we can do it stepwise. So, we can compute the derivative of loss with respect to output. Yes, because loss is a function of O. What will this give us? This will give us a gradient. Yes. Why? Because loss is scalar, output is a vector, we are differentiating this, so we get a gradient. What will the size of the gradient be? This gradient, remember, is a row vector, and the size of the gradient is the size of your output. Yeah. Now, suppose our loss was this function O minus Y norm square half, then if we differentiate it, we will see that our derivative of loss with respect to output is simply, this O minus Y. We will later do this in practice and, as homework, and we will see why this is the case. This will be an assignment, but just believe me, and it will be the transpose of this. Why? Because it's a row vector. So, what will be the size of this gradient? The size of this gradient will be one row, and how many columns? Columns the same as the dimensions in my output. So, let me write it as dim of O. Yes. So, this is the gradient, and we are starting the chain rule. What do? We backpropagate. We call this the derivative of loss with respect to output, and we are sending it to the previous layer. And again, as one of the main assignments of the week, what we will do is we will implement this whole thing, the chain rule, the forward, the backward for a few layers, and then actually train a neural network based on that. So, and we'll talk about that separately, because what happens is each of these module is very independent. All it does is the forward pass. So, each of these modules, right, let's assume it's this module. Remember, it essentially has the forward function, and what does the forward function take? It takes in the input, right, and what does it give? It gives us the output. And then we also have the backward function. And this backward function is essentially two functions. And what does the backward function take? It takes in the input and it also takes in the gradient which is coming in from the next layer, and it then calls two functions. It does, the gradient, so it does the input, so we'll look at it in detail later, but it does something where it then backpropagates to the input, and it does something where it does something to the weights, right? So it then backpropagates to the weights, but we will see this later. But the only thing I want you to know is each module is very independent. All it needs to know about is what is coming into it, and and it can just be very independent, and we'll see that when we code it up. But for now, let's just look at the theory of it. We will look at the practice of it, we will look at how to code it up, and we will actually train the neural network. We will actually write a short version of PyTorch. Yeah, so what we can, so we had computed this gradient, and the good news is that we can also find the derivative of output with respect to weights. Why? Because output is a function. It's some function of what? It's some function of my input A4 and my weights W, right? So since we have our gradients here, and the size is, it's a row vector, the size is that of O, and the good news is that we can also compute the derivative of our output with respect to the weights. Why? Because the output here directly depends on my weights, right? Because my output is some function of my input, in this case A4, and my weights W5. So we can directly differentiate output with respect to my W5. Now output is a vector and W is a vector. So what will this give us? It will give us a Jacobian, right? And then in the Jacobian we will have the outputs component. So we have derivative of O1 with respect to the partial derivative of W1, and in the row it only has like O1, but it will have my Wn, and then the second row will be derivative of O2 by W1 and all the way to O2 by Wn and so on. So this is something that we know about. So what do we have? Our derivative of O with respect to W5 is a Jacobian. And what is the size of the Jacobian? The size of the Jacobian is the same as the size of output and the size of W5. So my Jacobian is a matrix that looks like this. The size is M cross dim of W5, right? Because we have m rows and each row corresponds to O1, O2 all the way to O of m. Yes, with respect to W, the different W's, W1 all the way to dim of W5. And what does any of these components signify? Like we said, since k is some differentiable function with respect to and what we want to say is, okay, each element kl of this Jacobian that we just calculated indicates how much will the kth output wiggle when we wiggle the lth component of the weight. So again we have our Jacobian, some element here is, let's say, partial derivative of O of k with respect to partial derivative of W5 of L, and what will it signify? It will signify, okay, how much will the kth component of my output wiggle, how much will that change when I change the lth component of my weight. Okay, so we have computed now the gradient dou L by dou O. We also have the dou O by dou W5 Jacobian, and now when we have these two, what we can do is we can very nicely multiply them, and that will actually give us the derivative of loss with respect to W5. So what did we do? We have our derivative of loss with respect to output, which was, remember, a row vector of size 1 cross m. So we keep it on the left, 1 cross m, and then we have our Jacobian of size m cross dim W5. So what we do is we multiply it, and what do we get as output? As output we get size 1 cross dim W5. So it is exactly the size of W5, and we can then use it to compute our quantity that we are interested in. What is the quantity we are interested in? We are interested in this quantity of derivative of loss with respect to W5, and the size is the same as W5 except that it's a row vector, and we can directly use it to update W, right? Because what we want to do is we want to say, okay, W5 is equal to W5 minus some lambda, which is the learning rate, and this derivative of loss with respect to W5. And this quantity is what we were interested in, and we got it through this backpropagation, through this chain rule. Why chain rule? Because we had to calculate two quantities, this one and this one. And why chain rule? Because you will see next. Right. So what we also want to do is we also want to send back these so-called these gradients to every layer, right. So what we have done now is we have computed the gradient of loss with respect to weights. We also have to compute the gradient of loss with respect to the input, and this is one of those functions that we will write when we write our own PyTorch. Right. So this gradient of loss with respect to input is something that we will send to the previous layer, and to compute that we also need to compute the gradient of output with respect to input, right. So not the gradient but the Jacobian. Why? Because the output and input, so the output and input are both vectors. So what we want to do is we want to compute the partial derivative of the gradient of the Jacobian of the output with respect to input, and input here is A4, and this will actually give us a Jacobian, right. And so what will that Jacobian signify? We know that each component of that Jacobian, so the k comma l component of that Jacobian will essentially tell us, okay, how much will the kth output wiggle when we wiggle the lth input, right. So this is what we want to do when we want to compute our this quantity, right. So this is good. So it's basically how much will the so it's basically what we discussed, how much will my kth component of my output wiggle when I wiggle the lth component of my input or the lth component of the output of the previous layer. Right. So what we do is, let's do it here fresh. So we have our derivative of loss with respect to output. This, as we know, is our row vector. This is the gradient. We just computed the Jacobian, which is the derivative of output with respect to input, and we then multiply it again, right. We multiply these things, and then what does it become? It becomes the derivative of loss with respect to A4. And this is the size of dim A4. It's again a row vector. It's this gradient, and this gradient we pass into this activation layer. Yeah. So we to every, so what our, so the function that we were writing, right, that PyTorch that we write, it takes in this gradient, and this gradient is given by my next layer. So this is the chain rule happening, and you'll actually implement it in practice. So this is why I'm talking about this in detail. But now, since this layer has no weights, it has no weights like this, right. So we can forget about doing the chain rule and actually computing what we need here. 1 second. So the only thing that our activation layers need to do is it needs to backpropagate. It needs to do this chain rule, and for the chain rule we need to pass in the gradients to the previous layer. So all we need to do here is compute the gradient. But how do we do that? We again need to compute the Jacobian of the output with respect to input, because we are able to do the output. Output is just a simple function of input. Let's call this j. So it's a simple function of input. We get a Jacobian, and what we do with this Jacobian is also very simple. What we do is we already have this quantity, you remember, our dou L by dou A4, which we had written as dou L by dou O into dou O by dou A4, and so we have this quantity already which came in from my next layer. And here what did I calculate? And remember, this is a gradient, so it's a row vector, and we multiply row vectors from the left. And what did we calculate here? We calculated this A4 by A3. And now when we multiply it, we will get what we want to pass into the previous layer. We will get this quantity, what is the gradient of loss with respect to A3. And this is what this activation layer will pass to the previous layer here. Yeah, so we'll see this. This is what we are doing here. So we computed the Jacobian, we computed this gradient, and this is what we backpropagate to the next layer, right? This is what we backpropagate to the layer 3. And this is what we had written down. So if you look at this, this is nothing but the partial derivative of loss with respect to A3. Yeah. So it's a gradient of loss with respect to A3. So we backpropagated it, and now my layer 3 has access to this. And why does my layer 3 need it? Because it needs this to calculate the derivative of the, the gradient for the weight, because it needs to go in that direction, the negative direction of the gradient, to then update W3. So this is why we have this interesting quantity from the next layer, and then this layer independently can calculate the derivative with respect to, the output of this layer with respect to the weights of this layer, right? Because the output of this layer is A3 and the input is A2 and the weights are W3, and because the output is a function of W3, we are able to find the partial derivative of A3 with respect to W3, which is again a Jacobian. Yes, because we know it's a vector by a vector, so it's a Jacobian. So we use that Jacobian which we just calculated independently by this layer. We use the gradient which is coming in from the next layer, and look what this gives us. This gives us actually this quantity, right? Because all this is kind of nullified, and once this is nullified, we get the loss by so we get loss by W3, and this is the quantity that we are interested in. Why? Because then we can update the weights with respect to the W3, but we are not able to find this derivative of loss with respect to W3 directly, and for this we did all this chain rule, and we started from the derivative of loss with respect to output, which is a gradient, and then we backpropagated, we did the chain rule, we kept on passing these gradients to the previous layer, and finally using the gradients coming in from the next layer and this Jacobian that we created of the output with respect to the input, we are able to find that quantity that we are interested in, the derivative of loss with respect to weight, and then we are updating this. And this will get clearer when we actually implement it. Another thing to note is that if you do the dimensions of the matrices and the vectors, you will find that the dimension of this is exactly the same as W3. Why? Because the Jacobian that we are multiplying it has this dimension, the gradient that came in from the next layer has this dimension. When you multiply it, it becomes 1 cross dim of W3. And this is why we can do that pointwise subtraction with that lambda, and we are able to update W3.